Hi, I'm Lockie. I'm one of the hardware section leads at MCAV, and together with Rowan, we will provide an insight into what the hardware section has been up to over the past few months. One of the first tasks the team attempted was to investigate the rewiring of our computation stack. This is where all the interconnections between the actuation, connectivity, and perception systems are housed. The intent was to improve both the cable management and cable routing. This would make all the hardware much more accessible. Components would be securely mounted and provide improved access to the ports on the devices. Hence, when students or staff members were undertaking various research tasks and wanted to test new hardware, this more modular design would make adding new sensors and devices more seamless. The initial design work for this has been completed, with the works expected to be undertaken early next year. Following this, the team investigated the current power management and power distribution systems, ascertaining how they can be improved and the possibility of leveraging the car's alternator to charge the batteries that runs our computation stack. The final key project the hardware section has been busy designing is the dynamic obstacle. The broad intent for this was to create a durable platform that can be used for testing a wide variety of scenarios. With the initial prototype, the intent was to use off-the-shelf components where possible. This was in order to create something with the shortest lead time possible. I will now hand it over to Rowan, who will delve into the team's current progress with the dynamic obstacle. Thanks, Rowan.
The hardware team began developing a prototype dynamic obstacle with the idea in mind that we could build a small remote-controlled vehicle that could be used for demonstration purposes by the Subaru to show its ability to sense and avoid different obstacles. We originally started looking online for a chassis we could build around, and we found a 6-wheeled RC car chassis that had pre-installed shock absorbers that we felt was perfect for our needs. On top of the chassis, we decided to use square hollow sections for the housing of the electronic components. Working off this chassis, we designed a small armor covering for the chassis to protect the electronics on the inside. Using magnets, we planned to purchase and attach a figure to the top of the covering to demonstrate the Subaru's obstacle detection capabilities. The electrical components of this prototype will use a Bluetooth module to communicate with an app installed on an operator's phone that will enable the operator to change the obstacle's direction. This Bluetooth module will be paired with the motors already in place on the chassis, and alongside the motor driver will allow us to develop a successful prototype once the team reconvenes in 2021. The prototype will be used as a proof of concept for a dynamic obstacle of MCAV. Once this prototype has been manufactured and sufficiently tested, we plan on producing a Mark II variant of the dynamic obstacle. This model will be built from the ground up by the hardware team and will encompass all of our learnings from the original prototype. Using SolidWorks, a design for the chassis and suspension modules were iterated and finalized. These are currently shown on screen. As you can see, that one of the early iterations in the top left-hand corner, and the current iteration as of December 2020 is in the bottom left-hand corner, with the final iterations suspension modules shown on the right-hand side. Unlike the prototype, this model has been designed to have the Subaru drive over it while remaining undamaged. To do this, significant time was put into the suspension design. The final design incorporates a suspension that uses a set of springs that can hold the predicted weight of the dynamic obstacle with minimal deflection. Once the car drives on top of the shell, an extra 400 kilograms will be added to the total mass of these springs, at which point they will deflect significantly. This will cause the base of the chassis, the dynamic obstacle's chassis, to hit the ground, at which point the dynamic obstacle will effectively become a static speed bump for the car. Once the car leaves the shell, this dynamic obstacle will spring back into its original position and assume its role as a dynamic obstacle once again. The shell of this Mark II dynamic obstacle is still being developed, with current simulations progressing. We hope to have a final shell design by the middle of semester 1, 2021. For the electronic side of the dynamic obstacle, we will be using lithium iron phosphate batteries to power DC brushless motors, which were chosen after a selection process to meet our goals. Namely, we wanted it to be able to move 50 kilograms of mass at around 20 kilometers per hour. These motors will be controlled by ESCs, electronic speed controllers, which have also been chosen during a selection process. Lockie and I would just like to thank the entire hardware team. We know this year's been very, very difficult, and we really appreciate all of the great work you've all been doing. And we'd also like to thank Andy Salter for his hard work as section lead for most of the year. Thank you.